Okay, so let me just get straight to our lecture because I am hoping that I will be able to cover a few extra slides that we missed last week because of the fire alarm. I'll try to explain it in enough detail. If we can't, then unfortunately we will have to drop at least one of the topics at the end of the natural language processing at the end of the course. I really don't want to do it. There's no assignment, there's no homework related to natural language processing, but it will be very interesting to at least cover it in at least a little bit detail. So the idea is last week, week 15 was completely just about the revision and a mock exam so that it's helpful for everyone to just, refresh everything what we have covered. I think we have already covered quite a lot in this course already. There is still quite a bit coming in the next coming few weeks: machine learning, computer vision, deep learning. I'm missing one more. Natural language processing, definitely. So machine learning and computer vision are going to be very interesting. I'm pretty sure we cannot miss that. But we have already covered several search problems, right? We have covered macro decision processes. We have covered reinforcement learning. We have covered already Bayesian networks in sufficient detail. So we will spend one more week on Bayesian networks, and then we'll talk about its properties and features today, which make them a really powerful probabilistic machine learning approach. Not only just machine learning, but inference or reasoning approach in the field of artificial intelligence. And I also said that Bayesian networks basically come with the most famous equation in the field of AI, Bayes rule. So we'll talk about Bayes rule a little bit today, but we're going to have to clarify, like how the chain rule and product rules basically work in Bayesian networks. So once I show you a few examples of Bayesian networks, all these chain rules, slightly modified version of chain rule. We have covered chain rule so far. Slightly modified version of the chain rule that is already implemented behind Bayesian networks, and how Bayesian networks still tell us that the combination or the product of, remember, product of marginal and some conditional distributions ends up having a large joint distribution that we can have. So with that joint distribution, we can answer several questions, and that's what we're going to talk about more today. But before that, we will have to make sure that we understand how the chain rule, product rule, and the conditional distributions are implemented in Bayesian networks. Okay, so we talked quite a bit about, so we first started with chain rule, right? We said that the chain rule says that the joint distribution is basically a product of the marginal distribution and then the conditional distributions of all the variables given the preceding variables, such as something like this: P of x1 up to xn is equal to P of x1, then P of x2 given x1, P of x3 given x1, x2, P of x4 given x1, x2, x3, and so on and so forth until the xn arrives, right? So what is our main purpose right here? To get the joint distribution. Sometimes we say that, yes, we can get the joint distribution. And as long as we have the joint distribution, we can answer all sorts of queries. Remember, we say we look at the giant table, we look at where the query matches, right? The evidence, where the query matches, we look at only those rows. And then we see what is the evidence variable, right? Like given the behind that bar, given, then we select only those rows where the evidence is given, and we simply just multiply them and add them, and then divide them and just like normalize and get the answer, right? But what if you have like 100 variables in your problem scenario? Joint distribution. Remember, we said that if there are n variables, and each variable has a domain D, then that means we will have to do n times D, right? Like D times D times D times up to n times. And the time and space complexity of this is D to the power n, right? Even if there is suppose that you have the problem scenario that has only, let's say, Boolean variables, like just yes or no, right? So their domain is 2. So the domain is basically the same as what we have covered in constraint satisfaction problems, right? The values that we can assign. to the instantiations of the variable. Even if you have Boolean variables, but suppose that you have 1,000 Boolean variables. The time and space complexity or time complexity or to store that giant distribution is 2 to the power 1,000. That's even beyond even normal computational resources in today's life. So we have to basically, the idea is, suppose that if we go with the chain rule, by the time you get to p of xn given x1 up to xn minus 1. So that means you're getting the giant conditional probability table or the probability table just one variable before the 1,000th variable. So chain rule is very helpful, but for giant distributions, we'll have to do something extra with the chain rule in order for us to be able to store the probability distribution. Otherwise, it's just the same as storing a really, really big, giant conditional probability table. So what we said that we look at the independence if the two variables are independent or not. But then we also found out that just the independence doesn't make much sense in real world scenarios. We have to find out the conditional independence, like if a variable is independent of the other variable, given some evidence variable. If we say that we basically found out an evidence about something, then two or more variables become independent of each other. That's very interesting. That's basically the smart rule behind Bayesian networks. That we say that if we find out some examples or some areas where we can get the joint distribution by dropping some of the variables from the given clause, then we can shorten, or we can, make the size of the joint distribution table much smaller. So all what we are doing is we're saying that sometimes we have a really giant distribution, probability distribution, right? Giant table. What we can do is, instead of storing that really big giant table, we can store some marginal distributions, some conditional distributions, and whenever we have a product of that, we get the giant distribution, right? Joint distribution. So instead of storing that, we can just do the reverse, or like a few ways to organize them to basically get the actual giant joint distribution. And we said that there are some cases where we said that traffic, rain, and umbrella. We looked at the very simple example was that traffic basically, or umbrella, was independent of traffic as long as we find out the evidence about the rain, right? So we said that in that case, if we said traffic, rain, and umbrella is simply a product of probability of rain, probability of traffic given rain, probability of umbrella given rain and traffic, but because umbrella is independent of traffic given rain, we can simply drop that from the given clause. So now you see here, this one was basically a joint distribution table of 3 variables, 2 to the power 3, right? Suppose that these are basically just Boolean variables, right? So we are storing this probability table as 2 to the power 3 entries, 8 entries, right? So something like this. So I said that our table will look something like this, okay? This is, let's say, rain, traffic, and umbrella. Rain, true, traffic, true, true, false, false, true, false, false, right? But then umbrella for true, true, false, true, true, and then 4 more entries for umbrella being false, right? So, and then we have the probability values. Here are the 8 values, which is 2 to the power 3. So we are storing 8 values, right? Make sense? Now, if we drop it, this becomes 2 to the power 2. So we're saving a lot of space by finding out the conditional independencies in our network, in our problem scenario. So Bayesian networks basically, or BaseNets, provide us with the graphical, these are the graphical models that help us express the conditional independencies, conditional independence assumptions. So we'll talk about that quite a bit today, okay? So two problems with full joint distribution tables, basically, unless there are only few variables, the joint distribution is way too large to store. That is what we just talked about, to represent, right? It is hard to learn anything empirically about more than a few variables, right? Suppose that if you have about 99 variables in the given clause, imagine how long your equation can be. It is hard to learn when there are a lot of variables that are involved. So Bayes nets basically a technique for describing complex joint distributions using simple local distributions. What are the local distributions? What we're trying to get is, in our Bayesian networks, we say that we only look at the conditional probabilities based on only the variables that are directly influencing a variable. We just ignore or we forget about the entire basically links, within our network. I'll tell you guys about what the nodes and the links are. But we only look at the variables that actually directly influence each other. Those are the local probability distributions. And we will talk about that with so many different examples, and we will find out what do we even mean by local distributions. Okay, so these are basically graphical models. Bayesian networks are graphical models. They really nicely describe how variables locally interact, and local interactions chain together to give global interactions. Okay, so in Bayesian networks, we have a set of nodes. Okay, each variable is described as a node. Okay, as a set of nodes, like one per variable, and then it's a directed acyclic graph. And I'll tell you guys why it has to be a directly acyclic graph. There shouldn't be any cycle within the graph. Acyclic graph. There shouldn't be any loop or any cycle within the graph. Okay, what I'm trying to say is, suppose that if you have 3 nodes, something like this, you cannot have this. Okay, there shouldn't be any cycle. If you have the cycle, your chain rule is gonna be destroyed. You cannot apply chain rule. Because if you try to write even just like, let's say this is x1, x2, x3, you cannot write chain rule about it. So you have to make sure that there is no cycle, all right? So what is the arc? Arc is basically the same thing as what we have done in CSP, constraint satisfaction problems. There's an interaction between 2 variables. They are just directly influencing each other, just like how you guys did in homework too. Yes. Right. So you see here, if I write P of x1, x2, x3, according to the chain rule, it should say P of x1, P of x2 given x1 times P of x3 given x1 and x2, right? This is what the chain rule says. According to this cycle, we cannot write that because P of x1 is given x3 here, right? So according to this, if you have cycle, you're not going to be able to write the probability distribution using chain rule. We have to follow basically chain rule and the product rule. So this is what a Bayesian network looks like. Insurance. So there are about, I don't know, 26, 27 nodes, something like that. And this network basically represents each variable's probability distribution and each variable's interaction with respect to just some of its local or direct influencers. Direct influencers. Something like this. Age has a direct influence on whether you're a good student or not. Okay. Age also, determines or influences the driving skill. All right. Basically, just like how good your insurance should be. So age also has basically a direct influence on risk aversion. By the way, this is just one proposed representation of an insurance problem using Bayesian network. You can have different links too. That's fine. This is one representation. So, and this is basically one feature and one also pain point of Bayesian networks too, because you can represent one case scenario or one problem with multiple representations of Bayesian network. It is going to be us who will have to determine what each influence actually means. Does it make any logical sense or no? Sometimes you can even have a complete reverse link, and that will still give us the correct probability distributions. But then it is basically from a logical point of view, you'll have to find out how hard it is to get the probability distributions of when the link is reversed or in a certain order. So we'll cover a few of those examples soon, okay? Something like this, your socioeconomic status determines if you have an extra car or not, right? Also, it influences what vehicle year you have. What sort of vehicle do you have, right? Your socioeconomic status basically also influences whether you have an anti-theft installed. And theft basically is influenced by whether you have an anti-theft device or not, right? So basically, it represents local interactions. It doesn't mean that if you have two nodes far away from each other, it doesn't mean that they don't have a local influence. Something like socioeconomic, it's way up there, but it has a direct influence on anti-theft. Okay, it has a direct influence on ruggedness. Okay, so you can represent Bayesian network with the help of set of nodes, arcs, and local distributions. And we'll talk about local distributions in just a few minutes. Okay, I'm gonna skip this because this is another, Bayesian network that represents, what might be the cause that your car won't start in the morning. Okay, for example, you may have no oil, you may have no gas, starter is broken. Maybe in the morning, you may have just no charging, right? Maybe the battery is dead. How old the battery is. The battery diet basically is determined or influenced by how old the battery is, right? So your battery might be flat. So all these, like different local distributions or local interactions that are affecting this node, and your answer might be like from this Bayesian network, you will find out like what is the probability of certain variables given that your car won't start in the morning. You might be, you might want to know about the cars. Okay, so I think I've already talked about it, that we have nodes as variables in the Bayesian network. We have interactions. They indicate the direct influence between the variables. They encode basically conditional probability distribution, conditional independence. Something like this. Remember we said that toothache is basically independent of catch, given that you have already have the evidence at cavity, right? We talked about it last time in the last class, and we can drop one of the variables. So arrows basically give us the direct causation. Arrows give us the direct causation within the Bayesian network. Okay, I'm gonna skip it because, as I said, that suppose that we have this network where cavity basically is affecting toothache. Cavity might determine if you have cavity, you might have toothache or you might not have toothache. There might be a direct influence of cavity on toothache and also on the cat. But weather, in this case, no matter whatever the weather is not going to affect either the cavity or any of these nodes. So that means weather basically is just a totally independent variable in this. I just threw one in to just show you that there's no direct influence of weather on any of these nodes. And then I said that toothache basically is independent. Remember this orthogonal? Toothache is independent of catch given cavity. And this is catch. That's how you write it, the conditional independence. This is something very important or very useful that we're gonna talk about in order for us to represent the Bayesian network. This is basically one of the most famous examples in AI books that is taught in many different campuses. This is the most famous example of Bayesian network. Okay, the alarm example. The two people in the example that you have in the books, like whichever book, the book that we are also following, they are actually John and Mary. John calls, Mary calls. There are two neighbors that you have. Because I recently moved in Riverside, so I just changed this example a little bit to my two neighbors. Two of my neighbors. One is Danny, and the other one is Todd. They both are actually really nice people. They're really nice guys. They helped me, have our house problems when I just moved like the same day. There was no gas, and I couldn't get the hot water. So Danny offered me to just go and take a shower in his house. But then I just took a shower with cold water. I was a little shy. But they are really nice too, really nice people. Now, suppose that, I'm at work. I'm at work right now, and my alarm goes off. My alarm goes off, all right? What happens is there might be a burglary at home that because of that, the alarm might go off, right? Or in that area, sometimes an earthquake can activate the alarm too. There might be these two possibilities, right? An earthquake or a burglary might activate the alarm at my house. Suppose that Danny calls me. He's like, hey, buddy, there's something going on. I just saw someone breaking in your house, right? He might call me, and he would hear the alarm, and then he would go out and see there's a window broken, because he can see from his window, my house's window, right? And he say he can see the window broken, then that means, okay, Danny calls me, right? Danny calls me, and then he just lets me know about about the burglary, or about the alarm going off. Todd basically can also hear the alarm, and can also give me a call, right? And say, oh, here, I'm also hearing an alarm in your house. There is something wrong. I don't know, either it's earthquake or burglary. There is something going on in your house, and he just gives me a call. Sometimes, you can design this network something like this. Let's say Todd doesn't like me as much as Danny likes me. And sometimes he just doesn't call me. He never calls me, but then if there is a problem, there's a 50% chance that he might call me, and 50% chance that he might not call me, right? Or he will see Danny running around and seeing and trying to call me, or seeing like he's trying to call me, and he's running around and he's trying to protect the situation. There might be a link from Danny to Todd too. You can do that. You can design that network, but this is the example that we are gonna talk about quite a lot in this lecture and also the next lecture. So this is one of the most famous examples that is covered in AI classes, especially in Bayesian networks. So what we have here is we have 5 variables, right? Alarm goes off, burglary, earthquake, Danny calls me, and Todd calls me, right? So I can say a burglar can set the alarm off, an earthquake can set the alarm off based on these arcs. You see here, these arcs, a burglar can set the alarm off, an earthquake can set the alarm off. The alarm can cause Todd to call, and the alarm can cause Danny to call, right? Simple, straightforward. And this is how it will look like, right? So behind each node in here, there is a conditional or marginal probability distribution that sits in there. Something like this. You say the area that where I live, where I purchased the house, there is basically only 1% chance that there will be a burglary. Let's say the burglary rate or crime rate is really, really low there, and it's a pretty nice area, and I can fill that in. Probability distribution, probability table, right? Earthquake, only just 2% chance. Right? Is it 2%? No, it's a 0.2%. Okay. 0.2% chance that there might be an earthquake. So these are the probability distributions that sit in there. Now watch, Todd and Danny, they have a direct influence, right? Alarm. So they are gonna have a larger table, 2 to the power 2, because there is a direct influence, right? So I say alarm goes off, or it doesn't go off, and Danny calls or doesn't call, right? So there are 4 entries, 2 to the power 4, 2 to the power 4 for Todd. And then the alarm basically has 2 parents. So it will have to be 8, which is 2 to the power 3. Just because it's Boolean, that's why I'm saying 2 to the power 3. If it had the domain D, then I would have said D to the power 3. Okay, so that's the worst or the most general case that that I will be able to find out how many entries a probability distribution table will require. So here I have 8. And where does this live? It lives right under the alarm node. So each of these probability, each of these nodes basically have these probability distributions. And then using this probability distribution, we can answer several questions. Probability that, let's say Todd calls given the alarm goes off, probability that Danny calls given the alarm goes off, and probability that alarm goes off given that there is a burglary and earthquake. Or you can just put the instantiations like plus B minus E, minus B plus E, all sorts of questions you can answer using these giant distributions, conditional probability distributions, right? How can we represent this network? Something like this. Hold on. Limited mode. So this is the software that I usually use to represent vision networks. Let's see this one. Okay, it's called Neta. Oh, Netica. Okay, Netica. What I had was burglary. I just put the conditional probability tables just like that. You see here, table, and I say there's Netica. Netica, yes, it's free. You can also purchase it, but with the free version, you can have up to 20 nodes. Up to 20 or less number of nodes. If you have a Bayesian network that can be represented by 20 or less nodes, you can use the free version. If you have more nodes, then you will have to purchase it. But it's a really nice software that I've been using for a very long time. Okay, so yeah, you just say go to Netica download. Netica download, they provide you a jar version. This is a jar file. They provide you with the executables that you can download. Okay, executable then you. So I can say there is a 1% probability that there might be. So I filled those tables in. So what I did was, you see here, all what I have to do is I have to go and create a node, right? Add nature node, and I'm going to say I'm going to add 2 more states. Add state. This is slightly table, and I'm going to say state 0. It's a chance node. Where? Oh, okay, hold on 1 second. Where is the properties? Right above. No, there's an easy way. There's an easy way to add more states. State 0, new. So I have state 0 and state 1 now. I'm gonna say input state icons. So I'm gonna say state 0 as, let's say, true. Oh, I'm in a tablet mode. I can't write it. But what I'm saying is you can create a node and you can assign a probability distribution behind it. And as soon as you're done with this node, and suppose that this other node also influences alarm, all what you have is have to do is just create a link like that. That's it. Okay, so now that I've done this, I hope that the entire example has not been messed up completely. So where is it? Compile. So alarm network, it will show you the entries like this. So like 1, 2, 3, 4, 5, 6, 7, 8. So I'm saying that if there is a burglary and there is an earthquake and the alarm going off, suppose that the alarm is really good. 99% of the time, if there's a burglary or there's an earthquake, the alarm will go off. It's a pretty good alarm, right? If there is a burglary, then it will also go off. If there is an earthquake, there is an 80% chance that it will go off and 20% chance that it will not. And false, if there's no burglary, no earthquake, everything will be okay. 99% of the chance that it will not go off. So I actually put those probabilities in by myself. And what we will have to do is, now you see, suppose that I'm gonna say, Danny calls me. Suppose that I say Danny calls me, I'll click that. Suppose that Danny has called me, all right, then that means Danny has called me. See how the probabilities basically have changed a little bit from 3 to 6, then that means there might be some probability that the alarm has gone off. I think its probability tables have, let me see how I put it. So if the alarm goes off, there's a 99% chance that he's gonna call me. Even if it doesn't go off, Danny is a really nice guy. He still just sometimes calls me to talk to me, which is nice of him. And then we have the table of Todd. If there's an alarm, he'll call me. Otherwise, there will only be 20% chance. He might be at work, or he might not like me as much as Danny likes me. So I put all these probabilities together by myself, and I'm going to say that if Danny calls me, the probability certainly goes up, right? And the probability of the burglary, basically from 1%, it will go to almost 2%. So these probabilities change. That means there is actually a dependence. Danny's node basically is dependent on alarm, but then alarm is also conditionally dependent on burglary. Now let's say that alarm goes off. Now you see this, both these guys are going to call me for sure. And then also the alarm basically is affected by burglary or earthquake, right? So there are these conditional dependence or conditional independence that we will have to, relationships that we will have to figure out within our network. Now suppose that, we say that there is basically a local dependence relationship, right? That's one case. Now suppose that if I say alarm goes off, okay? Now let's say Danny doesn't call me. Now you see what I'm saying is that Danny doesn't call me, it has no effect on Todd calls me or not. That means, remember we said that as long as we have the evidence at the alarm, Danny and Todd become independent. Danny and Todd become independent. There is no effect given the cause. So we basically have seen those. Remember, umbrella is independent of traffic given the rain. Now just assume that this was the rain variable and this was umbrella and this was traffic, right? So this is one case scenario. If I provide, so if I do Danny calls or not, there is no effect on these. So no chain, basically no chain effect anymore. So there are two of these. One very difficult and painful conditional independence relationship in Bayesian networks is this. Now you see here, as soon as we give the evidence here, these two become independent. Now watch what happens. You see that? Burglary. If we are changing it, this guy changes too, even though we have given the evidence here. That's called the V structure. V structure, and this is going to be the most tricky, painful conditional independence relationship that we will have. So our job basically in Bayesian networks is to find out these conditional independence relationships, right? And then remove the variables that basically have conditional independence equals true. So some of them are really simple, straightforward. This is the most trickiest one, where we say, if we have the evidence, then the two parents basically are still dependent on each other. As soon as I remove the evidence, then there's no relationship. You see, if I do this, it doesn't change. This one doesn't change, only this changes. So this is achieved using an algorithm called D-separation. D-separation. What we are trying to do with the D-separation is that in some nodes we provide an evidence, and then we take basically some kind of subpart of the entire network, we separate it because there is no influence. There is no influence of it So we just separate it. That's called the D-separation algorithm. That's what we're going to talk about quite a bit in this, in probably this part. Okay. I think I mentioned in the beginning of the lecture that the Bayesian network that you design, it will have to be basically, you will have to have the logic behind it, why you are creating a certain link within your Bayesian network. With some links, it might be much easier to logically provide the evidence or logically come up with the probabilities, or say, due to an expert, opinion or the way you perceive the word, it is much easier to, compute the probability distributions, rather like as opposed to sometimes when you do the reverse. We'll take an example. We'll just go through an example. Now, suppose that we have this network, rain, okay, R, that it rains, and T, there's a traffic. So one example of this network can be just like this, right? You can design this model, rain and traffic. So this is one model that you can come up with. The problem with this model is there's no basically conditional relationship. It's just like rain and traffic is just like, they're just independent. Just like you are flipping multiple coins, right? Multiple coins, they have no relationship with each other. There is no link, nothing. You can come up with just two values here, two values here. That is it. Now, but what you say is, here is one more logical model that you have, that rain causes traffic, right? If it is raining, then that means there are higher chances that you will see heavier traffic, right? That is more logical model that you can have. So that's when you will have, a probability table that has a conditional dependency or conditional probability table. Why this model is better? Because logically this makes more sense, doesn't it? Like if it rains, there might be higher chance that you will see traffic, heavier traffic. You can also do something like this. If you are seeing traffic, then you can implicitly or explicitly, you can say, infer that there might be raining, which is why we're seeing heavy traffic. You can have the arrow the other way, right? Arrow the other way. But coming up with that explicit explanation is much harder than this way, in this link. Rain causes traffic, right? So suppose that we have, all right. Let's just have a very quick exercise of creating a Bayesian network from just the variables that I'm just going to throw at you. Okay, suppose that we have a traffic variable, right? We have rain, which is what we have just seen, that rain causes traffic, right? Let's say we also have a node that low air pressure. We have a variable that we have seen. Let's say from the weather station, we are getting this information about the low air pressure. Which node will affect? Will it rain, right? All right. So there will be something like this. Roof drips. Rain, right? So let's say rain basically causes roof dripping, right? How about the ball game? Ball game does cause traffic, right? You might also have this link that if there is a lot of rain, your ball game gets canceled. That might also be a possibility, right? You can also create that link too. How about this? Just independent. It's just not gonna, it's gonna be a very, very weak link that if you are just trying to connect this with any of this, right? With any of the network. So you can have your own problem actually, and you can come up with a Bayesian network with the help of, several conditional independence rules. Okay, so I think I've gone over this. I'm gonna have a couple of minutes break, and then I'm going to explain the semantics of how you see this equation, how this is slightly, modified or slightly more more simplified version of the chain rule that we have. See, we're not seeing the probability of xi given x1 up to xi minus 1 anymore. We're only looking at parents of xi. So these are basically the two properties of Bayesian networks that we have that still holds the property that the entire joint distribution is represented by this equation instead of the chain rule. Okay, so I'm going to have a couple of minutes break. If you have any question, you can ask me, but let's have a 2-3 minutes break and then let's start with this. Okay, Ronald. Bayesian network? Yeah, doing Bayesian. Bayesian networks tell you, the feature of conditional independence and conditional dependence using the rows. CSPs don't. They don't tell you that, and they have a complete different algorithm that is implemented. That's called what was that algorithm called? Backtracking search. Yes, I haven't even gotten to the next few slides. All right, so what Bayesian network says is that the joint distribution basically the global semantics defines the full joint distribution as the product of the local conditional distributions. So instead of chain rule, what it says is that the local conditional distributions only given the parents. And why does this work? Because it is different from the chain rule now, right? And the product of the probabilities or the conditional distributions given only the parents work because we assume or we say we have to follow this like reconstitution of the Bayesian network is that the conditional independence assumption holds. As soon as we find all the conditional independence, relationships within the Bayesian network, we are actually left with this equation instead of the chain rule, only just the parents. Remember, we were saying that suppose that umbrella is independent of traffic given rain, right? Given rain. But before we had umbrella given rain and traffic, we dropped the traffic node from the given clause, right? So as soon as we have dropped all of those nodes from the given clause, the equation or the property that is left is actually this, not the chain rule anymore. So Bayesian networks property still holds as long as we have the assumption of conditional independence. Not just the independence, but the conditional independence. And then after what we have is conditional independence, we can answer all sorts of queries. Like, these like smaller ones are the instantiations, like true, false, right? So you can say like probability that that Danny and Todd both call me and the alarm has gone off and there's no burglary and there's no earthquake. Something like this. Doesn't it look like this? So you see here, probability that Danny, this joint distribution, doesn't it look like this? Probability that Danny given. So this is, let me just write it in a more, so Danny calls, given, alarm goes off, right? If we look at the Bayesian network, so Danny basically is dependent on alarm, right? And then probability times probability that Todd calls me, given that alarm has gone off, times the probability that alarm goes off, that now you see here, it is the child node of both the burglary and earthquake. So I'm going to say, given that there is no burglary and there is no earthquake, right? And then probability that no burglary, this one, and then probability of no earthquake, something like this. And all what you can do then is you can go to the probability tables like this. You see here, Danny calls, given that there is an alarm. Let me see if I have no. So then you can go to this table and find out the instantiations, the rows, put those values, and you will get the joint probability distribution. But based on only the conditional probability, local conditional probability distributions now. Not like that. probability that there is burglary, probability that E given burglary, probability that alarm goes off given burglary, and this times probability that Danny calls given A, B, E, times probability that odd given D, A, B, E. That's the chain rule, if you remember. We're only focusing on the conditional independence assumption, and we will come up with the product of only local conditional probability distributions now. So we have changed the equation from chain rule to this by holding the assumption of conditional independence as true. All right. How do we? Okay. I'm going to skip some of these coin flips, rain, traffic, and I'm going to get to this slide just to let you know how interesting it is to have the change the rows, basically the arrows. Suppose that we come back to this same old network, probability, of traffic is affected by rain. So we have this link between from rain to traffic. And now suppose that we have this probability distribution that we are looking at, the marginal distribution and the conditional distribution. Now, to answer this query, P of R and T, isn't it going to be P of plus R times P of plus T given plus R, right? Make sense? Okay, so P of plus R is 1/4 times P of plus T plus R, which is plus T plus R, this, right? 3/4. This is what? 3/16. So we can answer queries like that, even different queries. Joint distribution. Remember, joint distribution is the product of marginal and conditional distributions, conditional probabilities, right? So as long as you have that table, you can answer queries like this. Now, suppose that we answer queries. Where did I? Oh, this is minus T, sorry. Minus T, and for minus T plus R is 1/4, which is 1, like this, right? We can answer queries. All right. I have talked about it already. How about this? So we found the probability distribution, joint probability distribution. What if we do the reverse causality? What if the traffic affects rain? Just like what we have seen, that if we are seeing the traffic, then we can infer or reason about whether there is, if we are seeing that there is raining, and we can infer or reason about traffic or not. Suppose that this is the probability distribution. You plug in some numbers, you can compute them from weather station data or by, by whatever data that you have. You can fill in those probability tables. You can answer that question. Now watch. The probability distribution of traffic and rain is exactly the same as when the link was the other way around. So this is actually one of the salient features of Bayesian networks, that you can represent one scenario with multiple different representations of Bayesian networks. Both are going to be correct. Okay, they all are going to be correct. They all are going to give you the same probability distribution. It will have to be, based on the problem domain and the idea of what makes the most sense, what makes the logical sense, that basically, or what makes the logical sense and what makes it easier to get these values, the probability distributions. Now you say that probability that rain causes traffic, it might be much easier to get the probability distribution for that link than this one. Right? Then this link, it might be much harder to find the numbers or to find the probability distribution for this network. So it actually depends on how we represent the problem. Probability distributions are going to be the same. That's the beauty of Bayesian network, but that sometimes is also a painful point too. Okay. I'm gonna, for about 10 minutes, I'm gonna talk about how we can come up with the conditional dependence relationships. Let me tell you. So we have talked about this equation already, okay? That this is the property of Bayesian network that comes from basically the Bayesian network. So let me just have a recap. We talked about the conditional probability, right? Most often in our real world scenario, we answer a question like that, conditional probability. Like if an event has happened, right? What is the probability of another event that has happened given that some of the event has some already observed evidence that you have? Mostly you answer questions like this, like what is the probability of something that has happened given that I have observed something? So based on something else. So conditional probability, we have talked about that quite a bit, right? Then we have talked about the product rule, meaning that in cases when the joint probability distribution is really, really large, we can rearrange our joint probability distribution with the help of the product of multiple marginal and conditional distributions. We can still come up with the joint distribution, right? Then we had the chain rule. You know why chain rule works? You know why it works? Because now suppose that you have this, XYZ. So what would the chain rule say? It would be something like this, right? X times probability of Y given X, right? Times probability of Z given X and Y, right? So what is this? If you look at the product rule, isn't it this? Like, so probability of X and then probability of X given Y divided by probability of X, right? That's the conditional probability distribution. How about this? This is probability of X, Y, Z divided by probability of X and Y, right? Now suppose that X and Y are together a joint, a big variable, right? So now you see, as soon as you start crossing these variables, the left-hand side becomes the, no, not here. The left-hand side becomes the right-hand side. This is why chain rule works. If you start expanding those, the left-hand side becomes equal to the right-hand side, which is good. So what we have looked at is the independence, that if the joint distribution of the two variables is just the product of the marginal distributions of the two variables, then that means these two are independent. Or if we said that probability of X and Y given Z is the same as probability of X given Z times probability of X given Y. Meaning, if we have found, let's say we have found the evidence, or we wrote something like this, remember, X given Y is the same as probability of X. Meaning that if we have found the evidence at Y, like Y variable, it is not going to change the probability distribution of X by any means. The numbers are just going to remain the same. That means the X is independent of Y. Okay, Nathan.
Can you relax that conditional independence equality so that if it's a really small, maybe it's a really small number that they're conditionally independent, or they're dependent but not very much.
Not very much. Yeah. But idea is that idea is that there is no change that happens between the values, probability values, or probability distribution of x or y. Suppose that if it is just a millionth, like 0.00000001, then that means you can actually remove that link from your Bayesian network. If it is negligible, you're just basically free, or you're given the flexibility to actually remove that, to have that. You can consider it based on a given threshold, based on what evidence, or based on what principles you want to say that two variables are independent or dependent. Given the domain that you're trying to address the problems into, you can consider two variables independent of each other based on certain threshold, how much they are affecting each other. Okay, the ultimate goal is basically to answer the questions with the highest accuracy, predictive accuracy. So you would not want to go at a point where you say, if I remove this link, then the difference between the false positive or the answer is going to be, let's say, 20% or 40% large or something. That's gonna be problematic. So based on basically the domain and seeing how much of that conditional independence is going to affect the entire solution, you can call them independent or dependent. Right. Yes, correct. There are ways to design the Bayesian network structure based on the domain knowledge, based on the data that you have in hand, and based on both together. Sometimes you say that within the Bayesian network, let's say rain causes traffic, right? We can get, let's say, past year of data on traffic, like traffic given rain, right? Like from a weather station, let's say from Google, from weather reports. We can find out, and we can say, using this data, 95% of the times when it was raining, there was high traffic. So you can actually look at the data and compute the probabilities. Sometimes you may not have any data. In that case, you can have basically your own domain knowledge. You can say, based on my expert opinion, based on my knowledge that I have, I'm going to believe that certain variable is independent or dependent on another variable by this much of the frequency, or by this much of the confidence. You can combine both of them. Most of the machine learning algorithms don't do that, which is why Bayesian networks are called like really beneficial, advantageous over several other techniques, because it implements both the learning from the data as well as learning from domain knowledge together. So hopefully we will have time to discuss a few examples that that were done, that I just did in the recent past, that I can show you where in some of the parts I use the data, and in some of the parts I just use domain knowledge. Okay, so I think we've talked about this. I'm gonna go over. We talked about. Okay, 1 second. We talked about the alarm network example. How do these probability tables come up? And then answering queries, right? Like plus D minus E, blah, 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 blah. You can look at the links, and we can say probability that there is burglary. Since it has no parent, it's going to be like this. Probability that there no earthquake. Probability that plus A, now plus A is dependent on both the burglary and the earthquake, right? And then we have Danny doesn't call, but it is dependent on alarm, right? Times probability that Todd calls, given that it is an alarm. Now, all what you can do is, you see here, you can put the value, which is this 1 times minus earthquake, which is this value, right? Times plus A plus B minus E. Okay, where is it? Plus A plus B minus E. This one, right? This row. 9, 4 times minus D plus A minus D plus A times plus T plus A, this one. And whatever the answer is, you can basically calculate or compute the probability of a certain event. As soon as, as long as you have these probability distribution tables, you can answer several different queries. But how do we, so it was something like this. Oh, I already found that. Oh, this is minus E. Shoot, I made a mistake. This should be minus E. Okay, now that is correct. Right? As I said, that suppose that if there are n variables and each variable has a domain, we have to store d to the power n, right? And if there are Boolean variables, we will have to store only up to 2 to the power n entries, 2 to the power n entries, right? In the probability distribution tables. That's huge. Now, if we keep the assumption of only the conditional probability distribution, we can actually reduce the size to quite a lot. We will still look at the n variables, right? We will still look at the n variables, but we will only look at the entries of its k parents. Suppose that if we change now the scenario that how big is an n node net if nodes have up to k parents. Now remember the conditional probability distribution equation. Instead of chain rule, we have the probability of xi given its parents only. Now what we do is we still will look at n variables, but then we will only look at the k parents of each variable. So this k plus 1 is the probability of the variable itself plus its k parents only. So we can reduce the complexity, storage complexity from 2 to the power n to only n times 2 to the power k plus 1. So the smaller the number of parents in your Bayesian network, the smaller the probability distribution table you will have, right? Okay. Conditional independence. I don't think we have time to start because it's gonna take at least about 20 minutes to talk about the conditional independence. So I'm gonna stop here. We're gonna talk about several examples like this. And last time we talked about how alarm or how a variable is independent of another variable given some evidence. In Bayesian network, we will find out the conditional independence relationships that we have found out. Can we verify them or not? So we'll have to talk about the relationships that should be verified. And there are 3 different ways to verify those. Chain rule, causal rule, and common cause. Common effect, common cause, and chain rule. So we'll talk about that in Wednesday's lecture. Okay.